We're going to work a problem here to calculate pressure at depth. So we're given this problem here, and as usual, the first thing we do is just read through the problem. We don't try and solve it. And so it says in 1960, a Navy bathoscope descended to a depth of 10,912 meters, about 35,000 feet into the Mariana Trench in the Pacific Ocean. And we want to know what is the pressure at that depth. Assume that seawater is incompressible, and what was the force on a circular observation window with a diameter of 15 centimeters. So then the next step we want to do is reread the problem and list just the givens. So what is given in the problem? And so the descent depth is h, so we'll call that h is 10,912 meters. Now again, the trick to translating a word problem into a solvable math problem is you want to write the givens in terms of variables that you use that are going to be used in the math equations to solve the problem. So that's the givens, just the depth that the submarine or bathoscope descends to, and then the diameter of the window. And the next step we want to do is reread the problem and just list the finds, so what it is the problem's asking us to find. And if we read through the problem, it's A is what is the pressure at that depth. So A is we want to find P, and that is going to be the pressure at depth H, and the force acting on the window at that depth, at depth H. And that's going to be in newtons, and pressures in newton meters squared. So next thing we want to do is write our assumptions. So the key assumption here is that water is incompressible. This is actually a key assumption in fluid dynamics. And the equations are parameters we're going to need to solve this problem. I'll just go ahead and list this. And the first one is the pressure depth equation. So that's pressure, or Pascal's equation, equals the density times gravity times H plus the pressure above, or the initial pressure we're starting with at the surface. So that's equation 1. And then 1 atmosphere, or the pressure at the surface of the Earth, the air pressure, is 101.325 times 10 to the 3 Newton meter squared. And I got that from the different ways to measure pressure, which is a handout in Canvas. And you can see here that 1 Pascal equals a Newton meter squared, and 1 atmosphere equals 1.0325 kilopascals, or 1.0325 times 10 to the 3 pascals, as I've listed here, and then, or you can list that in Newton per meter squared. Then if I refer back to the BUFA, the presentation handout for the textbook, if you go to this slide here, you can see the equation for pressure equals, so what does this equation really mean? It means if we have a column of water that's of this area here, then the pressure that would be felt on the hand, for example, would be the weight of this column of water. But rather than condense this to a point mass, saying that weight equals mg, which is not practical for water because it fills the volume, instead we use density. And so what we would say is that the pressure here of the weight of the water, which pressure, if you recall, is force divided by area. So that would be a Newton meter squared. That force that would be felt on the hand due to this weight of water would be the pressure here. That would equal the atmospheric pressure at the top of the column, which is the net pressure of the atmosphere, the air pushing down on this column, plus the weight of the water. And the weight of the water is given by rho, which is the density of the water, times g, which is gravity, times h, which is the height of the column. So essentially, area times A is the volume, and then the density is the mass per volume. So this is another way of stating basically weight equals mg, but the only difference is the mass, we can't consider it a point mass, so we have to use this equation here. So that's where this equation comes from. So back to our problem, I have the pressure here. So just to sketch this out, after I've showed you what this means, is here we have the submarine. I'm just going to make it a sphere, and here's the surface of the ocean, and it's a depth h below the surface of the ocean, and then we have P naught is the atmospheric pressure here pushing down, and then we have the weight of this column of water pushing down on this submarine, so that would be the pressure given by rho GH. So the total pressure that's pushing down on the submarine, which would be P is going to equal the atmospheric pressure, because this is just vector math, right? We have one-dimensional vector math, so it's going to be the sum of the forces, so it's going to be P0 plus the pressure or the weight of the water, which is rho GH, density of the water times gravity times h. So I substitute into this equation 1 here. Pressure equals the density of the salt water, which is 1.03 times 10 to the 3, times gravity, which is 9.8 meters per second squared, times the depth, which is 10,912 meters, plus the atmospheric pressure, which is approximately 101 times 10 to the 3, and the units are Newton meter squared. And if you go ahead and plug this into your calculator, you would get that the pressure at that depth, at h, is going to equal. So this represents you can think of this as the force or the weight of the water, which is the force of the water. That comes out to be, because of the depth and the density of the water, it comes out to be about 110 times 10 to the 6 Newton meters squared. And then you can see that the atmospheric pressure is 101 approximately times 10 to the 3. So you can see this is 10 to the 6, 10 to the 3. So really the pressure of the water at that depth really dominates. In fact, you could even neglect this in the equation. It's not going to change your answer that much, because this is 1,000 times much more force than the force of the air of the atmosphere. And so then you get the pressure at that depth is 110.2 times 10 to the 6 Newton meters squared. And that's our answer. So that's incredible pressure. So part B is we want to find the net force acting on the submarine's window at this depth here. So here's the inside of the submarine, or the bathoscope. Here's our window, and we have a pressure pH acting on the window. Now let's just assume inside where the person is, or the people, that the pressure is at the surface pressure, P naught. So the net force, or the net pressure acting on this window, is going to be, we could say that the net pressure is going to be the difference between the force outside minus the force that's pushing back on the window, which is atmospheric pressure. So that comes out to be, essentially we take 110, let's just say approximately, 110 times 10 to the 6, which is pH, minus P naught, which is the atmospheric pressure, which we have here, which is approximately 101 times 10 to the 3. And that gives us this right here, the net pressure acting on the submarine's window, which is going to be, let's say, approximately 110 times 10 to the 6 Newton meter squared, approximately. But we want to know the force. What's the net force? And remember, force is in units of newtons. So again, by definition, pressure equals the force divided by area. And in this case, the area is the window, the area of the window. So the area of the window, which is a circle, and we're given the diameter. And I had input the wrong diameter. The diameter is 15 centimeters. And then the area of a circle, which is a circular window, is pi r squared. So it equals pi times the diameter divided by 2 squared. And if you plug those numbers in, I get an area of about 18 times 10 to the minus 3 meters squared. So now I'm ready to go ahead and calculate force. So force is going to equal the pressure times the area. And we can plug those numbers in. And that comes out to be about a force of 1.9 times 10 to the 6 newtons acting on that window. And that's equal to about 200 metric tons of force. So that's an incredible amount of force that's acting on that on the structure of the submarine and the window. So that's how you go about solving this type of problem. Also, note that one of the reasons I stress getting a calculator and becoming familiar with displaying it in either engineering or scientific notation. This is a good example of why you'd want to do that, because it's just the numbers involved. If you tried to do this with your calculator without using the exponent notation, it would probably run out of digits, and your accuracy would suffer. And to be consistent, this should be 1.94 since the input data was 3 significant figures, so the answer was within 3 significant figures. Now there's a similar problem maybe in the quiz where in this case it's an airplane above some distance above the Earth's surface h, and then you want to find the pressure, let's say on the window there or whatever, or cabin door, and it's the same process you would go through, except in this case the air pressure at that altitude is going to be very small or very low compared to the atmospheric pressure at the surface of the Earth. And then you go up a distance h. So the pressure here at altitude, is going to be less than the pressure at the surface. So what happens if you look at the inside of the airplane, you have a big pressure of the atmosphere pushing out, let's say on the door, and then you have a weaker pressure at this altitude pushing in, so the net pressure would be the difference. So the net pressure, again, is the same problem, would just be P out minus the atmospheric pressure. And if we're interested just in absolute value, then we would just take absolute value. So it's essentially the same problem, but it's looking at it from a different perspective. In this case, from an airplane. But again, you can see the pressure difference is pretty significant, because obviously at whatever the airplane's at, 10,000 feet or 20,000 feet, we couldn't survive at this pressure level because the air is so thin there wouldn't be enough oxygen. So the pressure on the outside is going to be much weaker. So and typically also on an airplane they don't pressurize at the surface pressure. They usually pressurize, I think, at about maybe 4,000 feet on an aircraft. So the internal pressure on an aircraft is about 4,000 feet. And that's why when you fly long distance, sometimes you get fatigued, because you're really flying inside is at about 4,000 feet. The air is drier. That's why they say drink a lot of water when you're flying. And then the newer planes, I believe, the 787, which is graphite composite, they can actually pressurize it at a lower pressure, because they want to keep the interior dry because of some of the steel and things like that can rust. But graphite composite aircraft, they don't have that problem, so they would operate at a lower pressure, which in theory is supposed to make your flight more enjoyable and you don't get as fatigued because the cabin pressure is lower than it normally would be. And that concludes this problem. Thank you.